JPL has developed new omnidirectional anchors to enable mobility on natural rock at any orientation in any gravitational field. These anchors are based on microspine technology. Microspines are made using shape deposition manufacturing, an iterative milling and casting process that yields unique multi-material parts with embedded components. Anchors use a new hierarchical configuration of microspines, with 16 independent carriages each housing 12 microspines. Torsion springs bias these carriages into the rock surface, and an engagement degree of freedom drags the spines across the rock, establishing an anchor, seen here lifting a 13-kilogram rock. A disengagement degree of freedom releases the anchor with less than 10 newtons of force. A second prototype uses the principles of microspines, but replaces elastomeric materials that embrittle in the cold temperatures of space with 80 steel extension springs inside the central housing. It's seen here lifting a 9-kilogram rock. Notice the independent motion of each of the spines. The anchors are truly omnidirectional, supporting more than 130 newtons normal to, 150 newtons at 45 degrees to, and 140 newtons tangent to the rock surface. A rotary percussive drill is shown coring in an inverted configuration into a vesicular basalt rock. This demonstration constitutes a harder than 0G proof of concept. Here, a full drill sequence can be seen.
Ready? 3, 2, 1.
A self-contained anchor and drill has applications to lava tubes and cliff faces on Mars, and to asteroid and comet missions where there will be insufficient gravity to supply the necessary weight on bit. A custom coring bit drills a 20 mm diameter borehole to a depth of 83 mm, while retaining a 12 mm diameter core. Drilling was also performed in a vertical, gravity offloaded configuration. Future work will focus on refining the robotic ankle for vertical and inverted climbing tests with the robot Lemur 2B.